Tonight we're going to explore one of the strangest questions in astronomy. It sounds simple, almost childlike in its innocence. Where does the Milky Way end? At first the question seems straightforward. Every object we know appears to have a boundary. A continent ends at the ocean, an island ends at the shore. A planet ends where atmosphere gives way to space. Even a star has an outer layer, however diffuse, beyond which its identity begins to dissolve into surrounding emptiness. Boundaries help the human mind organize reality. They tell us where something begins, where it belongs, and where it stops. So naturally, we assume our galaxy should obey the same logic. Somewhere there must be an edge. Somewhere the last stars must fade into darkness. Somewhere there should be a final border separating home from everything beyond. But the Milky Way resists that intuition. Imagine standing far above the galaxy, impossible as that may be looking downward from intergalactic space. Beneath you hangs a vast rotating spiral of light. Hundreds of billions of stars glow in enormous sweeping arms. Clouds of gas stretch across thousands of light years. Dense star nurseries pulse with new suns. Ancient stellar corpses drift through dark voids. At the centre, a supermassive black hole anchors the entire structure through gravity so immense it governs motions across staggering distances. From far away the galaxy looks almost elegant, structured, defined, bounded. From far away the Milky Way appears to have edges, but humanity has never seen that view. That is where the problem begins. We are not outside the galaxy looking in. We're inside it, deep inside it. We live embedded in one of its spiral arms orbiting the galactic centre at roughly 230 kilometers per second. Every observation we have ever made of the Milky Way has been made from within the system we are trying to measure. We're attempting to understand the shape of a structure so large that light itself takes about 100,000 years to cross its visible disk while trapped inside a tiny corner of it. Imagine being born in a forest so large no one could walk from one side to the other in a lifetime. Trees surround you in every direction. Fog fills the distance. Mountains block the horizon. You have no map, no aerial view, no satellite image. Yet you are asked a seemingly simple question. Where does the forest end? You might walk for years and still see only trees. That is humanity's situation inside the galaxy. For most of human history, we did not even realize the Milky Way was a galaxy. Ancient civilizations looked upward and saw a glowing river of light stretching across the night sky. The ancient Greeks imagined spilled milk from the goddess Hera. In ancient China it became the Silver River. Across cultures people saw myth before structure. They saw beauty before scale. And perhaps that was understandable, because scale is the first thing the Milky Way destroys. Our sun feels enormous because it dominates every aspect of life on Earth. Yet the sun is just one ordinary star among hundreds of billions. Earth feels large because it contains oceans, continents, civilizations, and the full known history of life. Yet Earth is a microscopic fragment in the solar system. The solar system feels vast because even our fastest spacecraft require years to reach its outer planets. Yet the solar system itself is barely a speck inside the galaxy. Perspective collapses quickly in astronomy. A single light year equals about 9.46 trillion kilometers. The nearest star beyond the Sun lies more than 4 light years away. The Milky Way spans roughly 100,000 light years across its visible disk, perhaps more depending on how one defines its outer structure. Its thickness varies. Its halo stretches far beyond visible stars. Invisible matter appears to dominate its true mass. Even these numbers, however, conceal the deeper difficulty. The problem is not merely size. The problem is definition. What exactly counts as the galaxy? Is the Milky Way only the bright spiral disk we imagine in illustrations? Does it include the diffuse gas extending outward? What about ancient stars orbiting far above the disk in the galactic halo? What about invisible gravitational structures containing little or no ordinary matter? What about material stripped from dwarfed galaxies long ago and now drifting through space as stellar streams? Where precisely should one draw the line? A line sounds comforting. Nature rarely provides one. Consider a coastline viewed from orbit. It looks sharp. But walk closer and the boundary becomes messy. Sand becomes wet sand. Wet sand becomes shallow water. Shallow water becomes deeper ocean. There is no exact centimetre where land becomes sea. There is transition, not separation. The Milky Way may be less like a city wall and more like a coastline. But even that analogy may be too simple, because coastlines do not move on cosmic timescales. Galaxies do. Every second stars orbit. Gas collapses. Dark matter shifts. Satellite galaxies fall inward. Tidal forces stretch matter into long luminous streams. Collisions reshape entire regions. Structures we casually call stable are on cosmic timescales, turbulent and evolving. The galaxy is not a frozen object. It is a process. That means the edge, if it exists, may not stay still. A boundary that moves is difficult enough. A boundary that depends on what you measure becomes stranger still. Astronomers have spent centuries trying to answer this question. At first, many believed the galaxy ended where visible stars ended. Later observations suggested stars extended much farther than expected. Then gravitational measurements complicated everything. Matter we could not see seemed to dominate the galaxy's mass. Suddenly, the visible Milky Way looked less like the full galaxy and more like a bright island floating inside, something vastly larger and mostly invisible. And that is when the question changed. Humanity began by asking, where does the Milky Way end? Soon we were forced to ask something far more difficult. What if we have been measuring the wrong galaxy? Because it turns out the bright river of stars above us may represent only a fraction of what truly surrounds us. The visible galaxy may not be the real boundary at all. The stars we see may simply mark the inner region of a structure far larger than imagination first allowed. And if that is true, then one obstacle immediately appears. Before we can locate the edge of the galaxy, we need to understand something much more basic. How big is the part we can actually see? If the first obstacle was philosophical, the second is brutally practical. How do you measure the size of something when you're trapped inside it? That question haunted astronomy for centuries. Not because humans lacked intelligence, but because the galaxy is extraordinarily good at hiding itself. The night sky gives an illusion of openness. We look upward and imagine clear visibility into the cosmos. In reality, much of the Milky Way is obscured by itself. Vast clouds of dust drift between the stars, absorbing visible light and blocking entire regions from view. In some directions, we see deep intergalactic space. In others, vision simply ends in darkness, not because nothing is there, but because the galaxy has concealed its own structure. It is a peculiar situation. The very thing we're trying to observe interferes with observation. Imagine trying to determine the size of a city while trapped in its densest district during heavy fog. Towers surround you. Streets twist unpredictably. Lights glow in the distance, but many are hidden behind buildings. Some districts appear crowded, others empty, though the emptiness may be illusion. From street level, the city feels infinite. Only from above could its shape become obvious. Humanity has never had that luxury. For thousands of years, the Milky Way remained a luminous mystery. Then in the early 17th century, something changed. In 1609, Galileo Galilei turned a telescope toward the glowing band crossing the sky. What appeared to the naked eye as milky haze suddenly resolved into countless individual stars. The revelation was profound. The Milky Way was not cloud vapor or divine residue. It was a vast accumulation of stars packed so densely that human vision merged them into continuous light. That discovery solved one mystery and created another. How far did those stars go? By the 18th century, astronomers began attempting something unprecedented, mapping the galaxy from within. Among the most important was William Herschel. Working in Bath in the late 1700s, Herschel built increasingly powerful telescopes and counted stars in different directions. His logic was elegant. If more stars appeared in one direction, perhaps the galaxy extended farther that way. Fewer stars might indicate a nearer edge. In principle, the method seemed sound. In practice, it failed. Herschel concluded that the Milky Way resembled a flattened disk and that the Sun sat near its centre. The first part was broadly correct. The second was deeply wrong. He had made a mistake that almost every observer inside the galaxy is destined to make. He assumed visibility equaled reality. It did not. Dust had hidden enormous portions of the galaxy from him. That error matters because it reveals something profound about cosmic measurement. Data is not just limited by instruments, it is limited by perspective. Even brilliant reasoning can fail when observation itself is distorted. Herschel did not misunderstand mathematics. He misunderstood what the galaxy allowed him to see, and the galaxy allowed very little. Over the next century, astronomy improved dramatically. Larger telescopes arrived. Photography transformed observation. New methods emerged for measuring stellar distance. Slowly, the scale of the Milky Way expanded. Distances once measured in hundreds of light years became thousands. Thousands became tens of thousands. The galaxy kept growing. Then came one of the most important breakthroughs in cosmic history. In the early 20th century, Harlow Shapley studied globular clusters, dense spherical collections of ancient stars orbiting far beyond the galactic disk. These clusters were extraordinary because they served as gravitational landmarks. Instead of looking at ordinary stars scattered chaotically across the sky, Shapley examined large structures whose positions hinted at something deeper. He noticed something strange. Globular clusters were not centered around the Sun. They clustered toward a distant point in the constellation Sagittarius. That point marked something enormous. The true center of the Milky Way. Suddenly, humanity faced a humbling correction. We were not near the middle of our galaxy. We were far from it, orbiting roughly 26,000 light-years away from the center. Earth was not central. The Sun was not central. Our cosmic neighborhood was provincial. This was more than scientific correction. It was psychological displacement. Civilizations have repeatedly discovered that we occupy less privileged positions in the universe than we imagined. First, Earth ceased to be the center of the cosmos. Then the Sun lost centrality. Now, even our stellar neighborhood became peripheral. Each discovery reduced our cosmic importance. Yet paradoxically, each expanded our understanding. Once astronomers accepted our off-center position, the Milky Way structure became clearer. The galaxy appeared as a barred spiral with curved arms extending outward from a dense central bulge. Gas clouds traced these arms. Young blue stars illuminated active regions of star formation. Older stars populated thicker, more diffuse zones. Supernova remnants enriched interstellar matter. Stellar birth and death created a vast ecosystem spanning tens of thousands of light years. It finally seemed possible to define a border. Surely the spiral arms must end somewhere. Surely beyond the last major star-forming region lay emptiness. Surely a galaxy had limits. But once again, nature refused simplicity, because when astronomers pushed observations farther outward, something deeply unexpected appeared. The stars did not stop where theory predicted. Even stranger, entirely different stellar populations emerged. Ancient stars appeared far above and below the galactic disk. Sparse but gravitationally bound, these stars formed a diffuse halo surrounding the bright spiral structure. Some were among the oldest stars in the galaxy, survivors from the early universe itself. This changed everything. The Milky Way was no longer a disk with edges. It was a layered structure, a bright disk inside a thicker stellar environment. A stellar environment inside diffuse gas. Gas inside something even less visible. Every time astronomers thought they had found the outer border, another layer appeared beyond it. The boundary kept retreating. And then came the deepest frustration of all. Even if we could map every visible, stars might not determine the galaxy's true size. Because stars are not what hold galaxies together. Gravity does. That realization would transform the entire search for the galactic edge. It would force astronomy to confront a possibility few had anticipated. the most important part of the Milky Way might be almost completely invisible. And if invisible matter dominates the galaxy, then the visible spiral arms we admire in photographs may tell only a small part of the story. Which leads to the next question. If the Milky Way is far larger than its visible stars suggests just how vast is the structure we're actually living inside. To understand why the edge of the Milky Way remains so elusive, we need to confront the first enemy of intuition: distance. Not ordinary distance measured in meters, kilometers, or even planetary scales. Cosmic distance behaves differently because the numbers become so large that human experience stops being useful. The mind evolved to navigate forests, rivers, weather, and migration across landscapes. It did not evolve to reason comfortably about structures tens of thousands of light-years wide. And this matters because much of the difficulty in understanding the galaxy begins when intuition fails. Imagine shrinking the entire Earth to the size of a grain of sand. On that scale, the Sun would still be a sphere more than a meter wide, sitting over 100 meters away. Neptune would orbit several kilometers from that Sun. The outer boundary of the solar system would extend farther still. Even then, the nearest star beyond our Sun would remain thousands of kilometers away. Stars are not packed tightly. They are separated by extraordinary emptiness. This is the first misconception the night sky creates. Because stars appear crowded, we instinctively imagine density. But the galaxy is not a dense city of suns pressed close together. It is closer to isolated islands scattered across a cosmic ocean. That ocean dominates everything. In our region of the galaxy, the nearest stellar neighbour to the Sun is the Alpha Centauri system more than 4 light-years away. Light moves at roughly 300,000 kilometers every second. It circles Earth over 7 times in a single second. It reaches the Moon in just over 1 second. It reaches the Sun in 8 minutes. Yet even light needs more than 4 years to reach the nearest star. That alone begins to stretch imagination. Now expand outward. Our solar system orbits the galactic center at approximately 230 kilometers per second. That sounds unimaginably fast, and by human standards it is. A jet aircraft travels around 250 meters per second. The Earth itself orbits the Sun at around 30 kilometers per second. The Sun, carrying all planets with it, races through the galaxy at far greater speed. And still one full orbit around the galactic center takes roughly 225 to 250 million years. This number deserves pause. When the dinosaurs dominated Earth, the Sun occupied a different region of the galaxy. Since the emergence of complex multicellular life hundreds of millions of years ago, the solar system has completed only about 20 orbits around the Milky Way. 20. Civilization feels ancient because written history spans several thousand years. Agriculture stretches back around 10,000. Anatomically modern humans perhaps 300,000. Yet against one galactic year, all of recorded human civilization occupies less than a blink. This is what scale does. It changes what duration means. It changes what movement means. It changes what far means. The visible stellar disk of the Milky Way spans roughly 100,000 light-years across. Though some estimates extend larger depending on how faint outer structures are counted. Our solar system sits about halfway from center to visible outer disk. That means if humanity somehow launched a spacecraft toward the nearest visible edge at a substantial fraction of light speed, the journey would still dwarf civilization itself. Suppose for a moment we built a vessel travelling at 10% of light speed. That is around 30,000 kilometers per second, faster than anything humanity has ever engineered by many orders of magnitude. At that speed, reaching the visible edge from our position might still require hundreds of thousands of years. Civilizations rise and fall in centuries. Languages transform in millennia. Species evolve over millions of years. The galaxy measures journeys in tens of millions. Distance is not merely large, it is civilization breaking. That phrase matters because it introduces the deeper problem. Reaching the galactic edge is not just a transportation problem, It becomes an engineering problem, then a biological problem, then a social problem. Any attempt to physically traverse meaningful fractions of the Milky Way would demand systems capable of surviving durations longer than most species persist unchanged. A ship travelling outward would not simply carry passengers. It might carry civilizations, generations born aboard, languages diverging from Earth, cultures evolving in isolation, political systems emerging, collapsing, reforming, religions adapting to enclosed artificial worlds. Children learning of Earth not as homeland but myth. Distance changes identity, but there is a second challenge hidden inside the first. The galaxy is not static while you travel through it. This is easy to overlook. When people imagine journeys across space, they often picture destinations waiting in fixed positions. But stars move, spiral arms rotate, gas clouds collapse, satellite galaxies orbit, dark matter halos evolve. The Milky Way is a dynamic gravitational system. Over millions of years, structure shifts significantly. This means the edge you aim for today may not occupy the same position when you arrive. The target moves. The galaxy breathes. Even more unsettling, the Milky Way is not isolated. It belongs to the local group, a gravitationally bound collection of more than 50 galaxies, including the massive Andromeda galaxy. These systems influence one another across intergalactic space. Tidal forces distort outer regions, dwarf galaxies fall inward and are torn apart. Matter is exchanged, stripped, stretched. So even before we define the galaxy's edge, another complication appears. Which galaxy owns matter near the boundary? What happens when outer structures overlap? The clean mental picture of a luminous spiral surrounded by empty space begins to collapse. Instead, the Milky Way resembles a layered gravitational territory embedded inside larger cosmic flows. And then there is time. The light we receive from distant regions of our own galaxy is old. If we observe a star 50,000 light-years away, we do not see it as it exists now. We see it as it was 50,000 years ago, when human civilization had not yet built cities. By the time light reaches us, both observer and observed may have changed dramatically. Astronomy is never real time. It is historical reconstruction. We map the galaxy not as it is, but as it was at different moments distributed across space. That means even our best maps are temporal mosaics. Different regions are observed at different ages. The farther we look, the further into the past we see. And here lies the deeper revelation. Distance was never just about travel. Distance alters knowledge itself. It limits what we can know when we can know it and how accurately we can reconstruct reality. For centuries, astronomers believed that if they simply collected enough observations, the Milky Way's structure would eventually become obvious. But the more data arrived, the stranger the picture became. The galaxy did not resolve into a clean spiral with sharp borders. Instead, it became layered, diffuse, and increasingly ambiguous, which raises a troubling possibility. Perhaps the edge of the Milky Way is difficult to find not because we lack better measurements. Perhaps the problem is that we're searching for the wrong kind of boundary, because it turns out distance mayn't be the greatest obstacle after all. One deeper problem remained. We still could not clearly see our own home. It turns out distance was not the real problem. Distance is intimidating, but distance at least obeys mathematics. Once a scale is established, numbers can be calculated, trajectories projected, and travel times estimated. Distance may be overwhelming, but it is not deceptive. Visibility is, and the Milky Way is remarkably skilled at hiding itself. If an alien civilization living millions of light-years away were to photograph our galaxy, they would see something immediately recognizable. They would observe a barred spiral galaxy with luminous arms curving outward around a bright central bulge. They would measure asymmetries and gas distribution. They would map stellar populations by age. They would identify satellite galaxies. Most importantly, they would see the overall geometry in a single frame. Humanity has never had that frame. We live inside the photograph. That distinction changes everything. Imagine being inside a cathedral so vast that its walls vanish into darkness. Pillars rise higher than vision allows. Dust hangs in shafts of faint light. The architecture is magnificent but fragmented. You can see pieces of arches, fragments of ceiling, hints of corridors disappearing into shadow. You understand you're inside a structure of extraordinary scale, but you cannot perceive its total design. Now imagine the cathedral is moving. Its pillars drift. Its ceiling bends. Its walls distort over time. That is the observational problem of galactic astronomy. We are trying to infer architecture from fragments. For much of the 20th century, astronomers depended heavily on visible light. That worked well for nearby stars, but visible light has a weakness. Interstellar dust absorbs and scatters it. Dense dust lanes stretch throughout the galactic disk, especially toward the center, blocking enormous regions from direct observation. The galactic core, one of the most important regions for understanding structure, remained largely hidden behind thick curtains of dust. In practical terms, the Milky Way was obscuring its own blueprint. This created an almost paradoxical problem. The brightest concentration of stars in our galaxy existed in a region we could not properly observe with ordinary optical astronomy. We knew something enormous was there. We knew stars orbited around an unseen center, but crucial details remained concealed. Then new windows opened. Radio astronomy transformed the search. In the 1930s and 1940s, astronomers began detecting radio emissions from celestial sources. Unlike visible light, radio waves can pass through dust far more effectively. Suddenly, regions previously hidden became accessible. The galaxy started revealing structures invisible to optical telescopes. One of the most important discoveries involved neutral hydrogen. Hydrogen is the most abundant element in the universe. Large clouds of hydrogen gas permeate the galaxy, especially in spiral arms. Crucially, hydrogen emits radio signals at a characteristic wavelength of 21 centimeters. By mapping these emissions, astronomers gained a new method of tracing galactic structure. It was like turning on a hidden illumination system inside the galaxy. Spiral arms became easier to infer. Gas flows became measurable. Rotational patterns became clearer. Regions once lost in darkness started emerging from the fog. For a moment it seemed the great cartographic challenge might finally be solvable. But then the data introduced new complications. The Milky Way refused symmetry. The disk was not perfectly flat, it was warped. This detail sounds minor until its implications become clear. Imagine a vinyl record slowly bending upward at the edges. Now imagine that record contains hundreds of billions of stars, gas clouds spanning thousands of light years, and gravitational influences from surrounding galaxies. The Milky Way's outer disk is not a pristine plane. It bends, twists, and ripples. Why? That question remains deeply important. Part of the distortion appears to come from gravitational interactions with satellite galaxies orbiting our own. Among the most influential are the Large Magellanic Cloud and Small Magellanic Cloud dwarf galaxies, gravitationally bound to the Milky Way. Though small compared with our galaxy, their motion through surrounding matter can perturb outer structures. Even small companions can reshape giants over cosmic time. That insight changed how astronomers thought about edges. An edge implies stillness. Warp implies force. Force implies interaction. Interaction implies that what we call the Milky Way cannot be understood in isolation. Already, the neat picture of a galaxy ending at its visible perimeter was beginning to collapse. Then infrared astronomy pushed the story further. Infrared light penetrates dust more effectively than visible wavelengths, allowing astronomers to see stars hidden behind dense obscuration. Observatories operating in infrared revealed structures previously invisible, especially near the galactic center and inner spiral regions. The more wavelengths humanity used, the more layered the galaxy became. Optical telescopes showed stars. Radio telescopes showed gas. Infrared revealed obscured structure. X-rays exposed violent high-energy environments. Each wavelength produced a different Milky Way. This created an unsettling realization. There is no single visible galaxy. What you see depends on how you look. The Milky Way in visible light is not the Milky Way in radio. The galaxy in infrared is not identical to the galaxy in X-rays. Different instruments reveal different components of one underlying system. Home itself became observationally plural. That matters because defining an edge now becomes even harder. Which boundary counts? The boundary of visible stars, the boundary of hydrogen gas, the boundary of ionized plasma, the boundary of gravitational influence. Each measurement produces a different answer, and still one problem remained even after multi-wavelength astronomy transformed galactic mapping. Stars at great distances continued to appear where simple models predicted there should be far fewer. Ancient stars drifted far above the disk. Globular clusters orbited at enormous distances. Sparse stellar populations formed diffuse halos extending well beyond the bright spiral structure. The visible galaxy kept stretching outward. Then came an even stranger clue. Astronomers studying outer stellar motion noticed something profoundly difficult to reconcile with ordinary matter alone. Objects far from the galactic center were moving too fast. According to classical expectations, orbital velocity should decline with distance once most mass lies inward. That happens in planetary systems. Outer planets move more slowly because the Sun contains nearly all the system's mass. Galaxies should behave similarly. But the Milky Way did not. Its outer regions refused to slow as expected. Something unseen appeared to be exerting additional gravitational influence. And if gravity remained strong far beyond visible stars, then the structure surrounding us might be vastly larger than every map built from light alone. The galaxy was no longer merely hard to see, it was becoming impossible to define using visible matter at all. But because the more carefully humanity observed home, the more one disturbing conclusion emerged. The stars might not be telling the real story. Something invisible was shaping everything. By the middle of the 20th century, astronomers found themselves confronting a difficult truth. Light was no longer enough. For centuries, the history of astronomy had largely been the history of better vision. Larger telescopes gathered more photons. Better optics improved resolution. New wavelengths extended perception beyond the narrow range of human sight. Again and again, progress came from seeing more. The assumption behind that progress felt reasonable. If enough of the universe became visible, its structure would eventually reveal itself. But the outskirts of the Milky Way refused to cooperate. The more astronomers searched for a clean outer boundary, the more diffused the galaxy became. Instead of an obvious perimeter, they found layers of structure fading gradually into darkness. Spiral arms gave way to sparse stellar populations. Dense star-forming regions yielded to ancient halo stars. Bright matter became faint matter. Faint matter became near emptiness. And yet even near emptiness was not empty. That distinction became crucial. The first clues came from stars that did not behave like ordinary disk stars. Most stars in the Milky Way's disk move in relatively orderly orbits around the galactic center, largely confined to the flattened plane of the galaxy. Halo stars were different. They travelled on elongated, tilted, sometimes chaotic paths, plunging through the galactic plane before rising far above or below it. These stars seemed to belong to a different history. They were old, very old. Many contained extremely low concentrations of heavy elements, indicating they formed early in cosmic history, before repeated generations of stars enriched the galaxy with carbon, oxygen, iron, and other heavier elements. Some were relics from epochs when the Milky Way itself was still assembling. In a sense, these stars were fossils. They preserved memory. Every halo star carried evidence of a younger universe. This mattered because fossils reveal origins. Astronomers began to suspect that the galactic halo was not merely a diffuse extension of the disk. It might instead represent an archaeological record of how the galaxy formed. Ancient stars, globular clusters, and stellar debris could reveal past mergers, collisions, and accretion events. That idea transformed the search for the galactic edge. The outer Milky Way was no longer just a geometric question. It became a historical one. How was the galaxy built? Because if galaxies grow by consuming smaller systems, then their outskirts should contain scars. and scars were exactly what astronomers began to find. Across the halo, faint stellar streams appeared. These were long ribbons of stars stretched across vast distances, often remnants of dwarf galaxies or globular clusters torn apart by tidal forces. Gravity had shredded these smaller systems over billions of years, dispersing their stars into elongated structures wrapping around the Milky Way. The galaxy was not pristine. It was cannibalistic. Over cosmic time, it had consumed neighbours. This realization changed our image of home. The Milky Way had long been imagined as a majestic spiral calmly rotating through space. In reality, it was also a dynamic predator continuously growing through gravitational capture. Small galaxies approached. Tidal forces stretched them. Their stars were stripped and redistributed. Eventually, their identity dissolved into ours. The outskirts of the galaxy were full of ghosts. Not metaphorical ghosts, stellar ghosts, remnants of systems that no longer existed as independent galaxies. And this raised an unsettling possibility. If the halo contains debris from consumed galaxies, then where exactly does the Milky Way end and another galaxy begin? The question was becoming harder, not easier. Then came the globular clusters. These dense spherical star clusters orbit far beyond the main disk, sometimes tens or even hundreds of thousands of light-years from the galactic center. Each contains hundreds of thousands, sometimes millions of stars packed into relatively compact volumes. Most are ancient, among the oldest known structures in the galaxy. Globular clusters posed a conceptual problem. They clearly belonged to the Milky Way gravitationally, but many lay far beyond the visible spiral arms. If these clusters count as part of the galaxy, then the galaxy extends far beyond what most people imagine when they picture the Milky Way. And if they do not count, why not? Already the word edge was beginning to lose meaning. Edges imply abrupt change. The galaxy offered transition. Transition layered upon transition. Stars became sparse but did not disappear. Matter became faint but did not vanish. Structure became diffuse but remained gravitationally meaningful. Then astronomers made a deeper realization. The halo itself was not spherical in a simple way. It was clumpy, structured. Some regions contained more stars than expected. Others showed unusual motions. Certain streams suggested recent mergers. Outer regions appeared dynamically active, not static. The halo was less like a smooth shell, and more like an evolving ecosystem shaped by ancient collisions and ongoing gravitational disturbances. This changed the emotional scale of the problem. The edge of the galaxy was no longer just far away. It was conceptually unstable. We had assumed galaxies behave like islands, but perhaps that metaphor was flawed. Islands have shorelines. The Milky Way resembled something stranger, a fog bank. Stand inside dense fog and you can identify thicker regions and thinner regions, but asking for the exact location where fog ends becomes difficult. Density fades gradually. Visibility improves slowly. There is no precise border, only transition from more to less. The outer galaxy began to feel like that. Not boundary, but fading. Not edge, but dilution. Yet even this analogy failed to capture the deepest problem. Because all of these structures, stars, streams, clusters, gas remained visible matter. Visible matter accounts for only a fraction of galactic mass. That fact would soon overturn everything. By the 1960s and 1970s, astronomers studying galactic rotation encountered a puzzle that refused to disappear. According to ordinary gravitational expectations, stars farther from the galactic center should orbit more slowly once most mass lies inward. The farther outward you go, the weaker gravity should become. But measurements said otherwise. Outer stars were moving far too fast. Not slightly too fast. Consistently too fast. Their velocities suggested something enormous surrounded the visible galaxy, providing gravitational pull without emitting light. Invisible mass. Massive enough to dominate the galaxy. If this interpretation proved true, the implications were profound. The visible Milky Way, the spiral arms, the stars, the glowing disk might represent only the luminous core of a much larger hidden structure. Humanity had spent centuries trying to map the galaxy by studying what shines. Now astronomy was being forced toward a startling conclusion. Most of the galaxy might not shine at all. And if that invisible structure extends far beyond the outer stars, then the edge of the Milky Way may lie not at the last visible light, but somewhere deep inside darkness itself. By the 1960s, astronomers believed they were finally close to an answer. After centuries of incomplete maps, distorted observations, and expanding galactic models, a relatively clean idea had emerged. It felt elegant, mathematically sensible, and reassuringly intuitive. If the Milky Way was a gravitationally bound collection of stars, gas, and dust, then its outer boundary should simply occur where that material becomes too sparse to remain part of a coherent structure. In other words, the galaxy should end where gravity begins to lose. This became the first serious modern boundary theory. It sounded reasonable because the logic mirrors ordinary experience. A city ends where population density drops below urban continuity. A storm ends where organized circulation breaks apart. A planetary atmosphere ends where gas becomes too diffuse to behave as atmosphere. By analogy, a galaxy should end where star density falls so low that the system effectively dissolves into intergalactic space. At first, this model appeared promising. Astronomers measured stellar distributions across the galactic disk. Star density clearly declined with distance from the center. The inner regions were densely populated. Spiral arms contained rich star-forming zones. Outer regions became progressively thinner. Plot the numbers, extend the curve, and eventually the distribution seemed to approach zero. That approaching zero looked like an edge, at least on paper. The model offered comfort because it restored something the human mind desperately prefers. A boundary. A place where one could point and say, here the galaxy ends. But there was a problem. The universe rarely respects convenient mathematics. The first issue appeared in the outer disk. According to simple density models, stars beyond certain radii should become exceedingly rare. Yet astronomers kept finding them. Faint stars existed farther outward than predicted. Gas extended beyond stellar concentrations. Star formation, though sparse, continued in unexpected regions. Instead of collapsing cleanly towards zero, density curves became messy and stubborn. The galaxy refused to taper neatly. Still, many researchers remained optimistic. Perhaps the problem was incomplete data. Outer regions were faint and difficult to observe. Better instruments might refine the curve and reveal the true cutoff. Then something more troubling emerged. Different components of the galaxy produced different boundaries. Stars suggested one edge. Hydrogen gas suggested another. Ionized plasma suggested yet another. The boundary moved depending on what one measured. This complication exposed a hidden assumption in the original theory. It assumed the Milky Way behaved like a single substance. It does not. A galaxy is not one thing. It is multiple overlapping systems evolving at different rates. Stars follow long gravitational orbits. Gas clouds collide and compress. Magnetic fields thread through plasma. Cosmic rays propagate through diffuse media. Stellar winds reshape local environments. Supernovae inject energy across enormous volumes. Each component responds differently to physical processes. As a result, no universal density threshold naturally appears. Even if stellar density becomes negligible, gas may persist. Even if gas fades, plasma may remain. Even if ordinary matter becomes sparse, gravitational influence may continue. The boundary theory was beginning to fracture. Then came the warp. As radio surveys improved, astronomers discovered that the Milky Way's outer disk bends significantly above and below the galactic plane. This was not a minor geometric inconvenience. It changed the meaning of outer region. A flat disk allows relatively straightforward radial measurement. A warped disk complicates everything. Distances depend on direction. Structures overlap visually. Density estimates become more uncertain. The galaxy's outskirts were not smooth. They were distorted. Distortion implies force. Force implies interaction. Interaction implies the edge cannot be understood independently from neighboring structures. Already the first boundary theory was under strain. but its fatal flaw came from motion. Astronomers began carefully measuring how stars and gas orbit the galactic center. Classical gravitational expectation suggested a simple pattern. In a system where most mass is concentrated toward the center, orbital velocity should decrease with distance. This is familiar from the solar system. Mercury moves faster than Earth. Earth moves faster than Neptune. The farther outward you go, the slower orbital motion becomes. Galaxies should behave similarly. Outer stars should slow down. They did not. This was not a subtle discrepancy. Across multiple galaxies, including our own orbital velocities, remained unexpectedly high, even far from visible centers. Instead of declining sharply, rotation curves flattened. Flat rotation curves changed everything, because flat curves imply hidden mass, a great deal of it. Enough mass to keep outer stars gravitationally bound at high speeds, enough mass to dominate galactic dynamics, enough mass to make visible matter a minority component. Suddenly the first boundary theory collapsed. Why? Because its core assumption was wrong. It assumed visible matter defined the galaxy. Visible matter did not. The luminous Milky Way, the stars, the glowing disk, the spiral arms admired in astronomical images might represent only the bright interior of a much larger invisible structure. The galaxy we see might not be the galaxy that governs gravity. That distinction is profound. Imagine visiting a city at night from the air. You see glowing roads, lit buildings, illuminated districts. You assume the lights show the city's true extent. But suppose 90% of the city is dark infrastructure underground. Tunnels, foundations, power systems, reservoirs, transit networks. The visible lights would reveal only the surface expression of a vastly larger machine. Astronomers were beginning to suspect something similar. The visible galaxy might merely be surface illumination. The real structure could be hidden. This introduced a far deeper obstacle. If most galactic mass emits no light, then traditional astronomy becomes insufficient. Mapping stars no longer guarantees understanding. Measuring gas no longer defines structure. Even sophisticated multi-wavelength observations may miss the dominant component entirely. The search for the galactic edge had entered dangerous territory. Not because the edge was far away, because the edge might belong to something we cannot directly observe. That realization forced astronomy into a new era. The question changed once again. No longer where do the stars end? No longer where does visible matter fade? The question became far stranger. What invisible structure surrounds the Milky Way and how far does it extend? Because if unseen mass dominates our galaxy, then the true edge may lie far beyond every map humanity had ever drawn, and that invisible frontier had a name. Dark matter. There are moments in science when a problem stops being a problem and becomes a warning. By the late 20th century, the search for the edge of the Milky Way had reached such a moment. Astronomers had tried increasingly refined models of stellar density. They had mapped gas clouds using radio astronomy. They had accounted for warped disks, diffuse halos, globular clusters, and tidal debris. Each improvement sharpened part of the picture. Yet a deeper contradiction remained untouched. Gravity was not behaving as expected. And when gravity refuses expectation, physics pays attention. The classical prediction seemed straightforward. In a gravitational system where most mass is concentrated toward the center, orbital speeds should decline with increasing distance. This is not an obscure theoretical detail. It is visible throughout familiar celestial mechanics. Inner planets move rapidly because they orbit close to the dominant mass of the Sun. Outer planets move more slowly because gravitational pull weakens with distance. Apply that reasoning to a galaxy and the expectation is clear. Near the dense central bulge, stars should orbit rapidly. Far outward, where visible stars thin dramatically, orbital velocities should fall. The rotation curve should rise near the center peak, then decline. That is what theory predicted. Reality disagreed. When astronomers measured rotational speeds in outer galactic regions, they encountered something extraordinary. Instead of declining, orbital velocities remained stubbornly high. Stars tens of thousands of light-years from the center were moving far faster than visible matter alone could explain. The curve flattened. At first many assumed measurement error. That would have been comforting. Instrument calibration issues, distance uncertainties, poor velocity estimates, misclassified stellar populations. Astronomers are cautious by necessity, and extraordinary claims demand exhausting ordinary explanations. So they checked, then checked again. Other observatories repeated measurements. Radio surveys of hydrogen gas extended velocity mapping farther outward. Other galaxies were studied. Spiral after spiral revealed the same pattern. The anomaly persisted. This was not a local oddity. It was universal. Galaxies across the cosmos appeared to contain more mass than they visibly possessed. That conclusion was deeply unsettling because it attacked something fundamental. Astronomy had always relied on light as proxy for matter. Bright objects contain stars. Stars contain mass. Summing visible matter should provide a reasonable estimate of gravitational influence. Now that assumption was failing. Light and mass were no longer aligned. This meant one of two things. Either gravity behaves differently at galactic scales, or enormous quantities of unseen mass exist. Neither option was comfortable. To understand the magnitude of the problem, consider a simple analogy. Imagine watching cars circle a city on ring roads. By measuring speed, you estimate how much infrastructure supports traffic. If vehicles at the outermost roads travel far faster than visible roads, bridges and support systems could sustain, you conclude. Something hidden exists underground. Additional highways, structural supports, or energy systems invisible from the surface. The motion reveals the invisible. That is what happened with galaxies. Stars became tracers of unseen structure. They moved as though embedded inside a much larger gravitational architecture. And the farther astronomers looked, the stranger that architecture became. Suppose the Milky Way's visible stars accounted for nearly all its mass. Then beyond the outer disk, orbital speeds should decline sharply. But they did not. Stars and gas continued orbiting as if a massive extended halo surrounded the entire galaxy. Not a thin halo, an enormous one, potentially several times larger than the visible stellar disk. This idea transformed the galactic edge from a visible question into a gravitational one. Perhaps the edge of the galaxy is not where stars end. Perhaps it is where gravity stops dominating. That sounds reasonable until one asks the obvious follow-up. Where does gravity stop? Unlike light, gravity does not abruptly vanish. It weakens continuously with distance. Every mass influences every other mass, however faintly, across vast cosmic scales. That means gravitational boundaries are inherently fuzzy. One object may dominate nearby motion while still being influenced by larger surrounding structures. Boundaries become zones of competition. This matters because the Milky Way does not exist alone in empty space. It inhabits a crowded gravitational neighborhood. The galaxy is part of the local group, a collection of galaxies bound together across millions of light years. The largest members are the Milky Way and the massive Andromeda galaxy. Each possesses enormous gravitational reach. Each influences dwarf galaxies, stellar streams, gas clouds, and surrounding dark matter distributions. The gravitational territories may overlap. If so, the idea of a clean galactic edge becomes even harder to defend. Where exactly does Milky Way gravity end and Andromeda gravity begin? The answer may not be a line. It may be a shifting frontier. But before astronomers confronted that cosmic boundary problem, they needed to understand the hidden mass itself. Who first made the evidence impossible to ignore? The answer leads to one of the most important figures in modern astronomy. In the 1970s, observations by multiple researchers, most famously Vera Rubin, pushed the rotation curve problem into undeniable territory. Rubin studied spiral galaxies with extraordinary precision, measuring how stars moved at different radii. Again and again she found the same result. Flat rotation curves. The outer stars refused to slow. Her work did not create the anomaly, but it made dismissal increasingly impossible. The evidence became systematic, repeatable, and overwhelmingly persuasive. Something massive and invisible surrounded galaxies. Something dominant. Something that reshaped cosmic structure. Astronomers gave this invisible component a practical name: dark matter. The term sounds dramatic, but its meaning is deliberately modest. Dark matter simply refers to matter that exerts gravitational influence while emitting little or no detectable electromagnetic radiation. It does not shine. It does not reflect light. It reveals itself primarily through gravity. That modest definition concealed radical consequences, because once dark matter entered galactic models, the Milky Way changed size overnight. The visible disk, perhaps around 100,000 light-years across, suddenly looked like only the luminous inner region of something vastly larger. The galaxy's true mass distribution might extend hundreds of thousands of light-years outward, perhaps farther. Humanity had spent centuries trying to locate the edge by following stars. Now, stars looked almost misleading. They illuminated only the core. The real galaxy might live mostly in darkness, and that realization created a deeper mystery. If dark matter dominates the Milky Way's structure, then finding the galactic edge no longer depends on telescopes alone. It depends on understanding something we still cannot directly see. The search had become stranger than anyone anticipated, because the edge of our home galaxy might be hidden inside an invisible halo surrounding us all. Once dark matter entered the story, the search for the edge of the Milky Way changed permanently. Before dark matter, the question felt difficult but conceptually familiar. Astronomers only needed better maps, better telescopes, and more complete surveys of visible stars and gas. The galaxy's boundary, though elusive, seemed like something observation would eventually reveal. Dark matter shattered that confidence, because now the dominant structure surrounding the galaxy might be invisible. This was more than a technical inconvenience. It was a philosophical rupture. For centuries, astronomy had advanced by extending sight. Every major leap came from improved observation. Telescopes enlarged human vision. Spectroscopy revealed stellar composition. Radioastronomy penetrated dust. Infrared uncovered hidden stars. Each revolution expanded what could be seen. Dark matter introduced a deeply uncomfortable possibility. What if seeing more still leaves you blind to the most important thing? That possibility forced astronomers to reconsider the Milky Way from first principles. How much of the galaxy is actually made of ordinary matter? The answer proved surprisingly small. Stars, planets, gas clouds, dust stellar remnants, nebulae. Every familiar astronomical object composed of atoms contributes only a minority of the galaxy's total mass. Estimates vary with model assumptions, but visible baryonic matter appears to account for only a fraction of the Milky Way's gravitational mass. The rest is hidden. Pause on that idea. Everything humanity has ever touched, every mountain, every ocean, every city, every spacecraft, every human body, every star visible in the night sky, all belong to the ordinary matter category. Yet ordinary matter may represent only a small portion of the structure surrounding us. The galaxy is mostly something else. That realization alters emotional perspective. For thousands of years, humans feared darkness because darkness concealed predators, cliff storms, and unknown terrain. Modern civilization reduced that fear with artificial light. But on cosmic scales, darkness returned in a more profound form. Not absence of light. Presence without light. Something is there. It shapes stars. It bends trajectories. It governs structure. But it remains unseen. This led to the modern picture of the Milky Way as a nested system. At the centre lies the dense bulge surrounding the supermassive black hole Sagittarius Asterisk. Surrounding that is the stellar disk where spiral arms contain most familiar visible stars, including our Sun. Around this disk lies the stellar halo containing ancient stars and globular clusters. Beyond all of that, according to current models, lies the dark matter halo. And this halo is immense, far larger than the visible galaxy. Here the scale shifts dramatically. The visible disk spans roughly 100,000 light-years across, perhaps somewhat more, depending on faint outer structures. But dark matter models suggest the Milky Way's gravitational halo may extend several 100,000 light-years outward. perhaps approaching or exceeding 1 million light-years in radius depending on how one defines the boundary. This is not a minor correction. It is a change in worldview. Imagine believing your city occupies 10 square kilometers only, to discover its infrastructure actually stretches across an entire nation. Roads, pipelines, energy systems, and transport corridors extend far beyond the visible urban core. Suddenly, the familiar city centre becomes merely a bright inner district of a much larger organism. That is what dark matter did to the Milky Way. The galaxy expanded without becoming brighter. But there was a problem. Astronomers still needed a way to define where the dark halo ends. And here the search became even stranger. Unlike visible stars, dark matter offers no sharp observational marker. There is no last glowing object, no final luminous cloud, no visible wall. Instead, astronomers inferred dark matter through gravitational effects on stars, gas satellite galaxies, and background light. Inference replaces observation. That introduces uncertainty. Where exactly does the halo stop? Different methods produce different answers. One method examines escape velocity. If an object travels fast enough to permanently leave the galaxy's gravitational influence, its speed reveals how much mass lies inward. Another method studies satellite galaxies orbiting the Milky Way. Their trajectories depend strongly on total galactic mass. Yet another uses gravitational lensing, observing how mass bends light from distant objects. Each method improves estimates. None produces a perfectly clean edge, because halos do not behave like solid spheres. They fade. Density decreases gradually with radius. Inner regions are dense enough to strongly dominate stellar motion. Outer regions become increasingly diffuse. Eventually, gravitational influence weakens relative to surrounding structures. But eventually is not a boundary. It is a transition. That word kept returning. Transition. The Milky Way refused edges and preferred gradients. And gradients are cognitively uncomfortable. Humans prefer categories. Land or sea, day or night, inside or outside, home or elsewhere. Yet nature often offers continuums instead. Dawn is not night or day, shorelines are not purely land or water. Atmospheres fade gradually into space. Now the galaxy seemed to behave similarly. The more accurately astronomers modelled dark matter, the less meaningful a hard boundary became. Then the problem deepened further. Dark matter halos are not perfectly isolated. Cosmological simulations suggested halos interact, overlap, merge, and accrete matter continuously. Smaller halos fall into larger ones. Tidal stripping redistributes mass. Streams of matter connect galaxies across cosmic filaments. The Milky Way's dark halo might not end cleanly because the larger universe itself is structured like a network. A network has nodes. Nodes have bridges. Bridges blur separation. This brought astronomers to a disturbing possibility. The edge of the Milky Way may not be a single boundary because galaxies themselves may be less isolated than human language suggests. What we call a galaxy could simply be a dense node inside a larger cosmic web. That idea felt abstract until satellite galaxies entered the story. Around the Milky Way orbit dozens of smaller galaxies. Some are stable companions, others are being torn apart. Their stars stream outward in long gravitational ribbons. Their dark matter interacts with ours. Their trajectories preserve clues about the shape of the surrounding halo. And those clues pointed towards something unsettling. The outer halo was not smooth. It was structured, clumpy, dynamic, still assembling. The Milky Way was not finished forming. Even now our galaxy continues growing. That meant the edge, whatever it was, could not be fixed. It moved. It evolved. It changed across cosmic time. The search for the galactic boundary had reached a strange conclusion. The more precisely astronomers measured the galaxy, the less the word edge seemed to apply. Yet one hope remained. Perhaps large-scale observational missions could map the outer structure with unprecedented accuracy and finally constrain the halo. Humanity would need better data, better surveys, better instruments, and so began a new phase in the story. The era of missions designed to map not just stars but the hidden architecture they'd revealed. But those first grand attempts would not bring clarity. They would make the outskirts stranger still. By the end of the 20th century, astronomy had entered a new era of ambition. The problem was no longer lack of curiosity. Humanity now understood the scale of the challenge. The edge of the Milky Way could not be found by simply pointing larger telescopes at brighter stars. The visible disk was only part of the story. The halo extended far beyond ordinary observation. Dark matter dominated mass while refusing direct detection. Stellar streams hinted at ancient mergers. Satellite galaxies carried clues about invisible gravitational architecture. The challenge had become civilization-sized. If humanity wanted to understand the true structure of the Milky Way, it needed something unprecedented. Not isolated observations, not individual telescopes, not small regional surveys. It needed comprehensive mapping, a census of the galaxy. That idea sounds simple until one confronts the numbers. The Milky Way contains hundreds of billions of stars. Even if only a tiny fraction could be measured precisely, the required dataset would still dwarf anything astronomy had attempted before. Positions, distances, velocities, brightness, spectra, chemical signatures, orbital histories, cluster memberships, stellar ages. Every star could become a data point in a vast gravitational reconstruction. The dream was audacious. Map enough stars and invisible structure would reveal itself through motion. In theory, this would allow astronomers to infer the shape of the dark halo and perhaps identify the galaxy's true outer reach. In practice, the first grand surveys delivered something less satisfying. They produced complexity. The outer galaxy became messier with every dataset. One of the early major breakthroughs came through wide-field sky surveys, especially digital surveys capable of systematically cataloguing huge numbers of stars. Instead of targeted observations of specific regions, astronomers began scanning large fractions of the sky with consistent instrumentation. This changed the nature of discovery. Rare structures hidden across vast areas became detectable because patterns emerged statistically. And patterns did emerge, but not the ones many expected. Instead of revealing a smooth outer halo, surveys exposed substructure everywhere. Stellar overdensities appeared where smooth models predicted uniform distributions. Streams wrapped around the galaxy like torn ribbons. Dense clumps suggested merger remnants. Unexpected stellar populations appeared at large distances. Outer regions looked less like equilibrium and more like aftermath. The galaxy's outskirts resembled debris fields. That was the first failure. The mission to simplify instead revealed chaos. Yet chaos can still contain information. Astronomers refined simulations, hoping observed substructures might align with theoretical merger histories. Computer models grew increasingly sophisticated. Entire galaxies could be evolved numerically across billions of years, incorporating gravity, gas dynamics, star formation feedback from supernovae and dark matter halos. These simulations produce striking insights. Galaxies do not grow quietly. They assemble hierarchically. Small systems merge into larger ones. Larger systems consume smaller neighbors. Outer halos retain fossil evidence of these events. Smooth structures become rare because accretion is ongoing. The Milky Way's outskirts should naturally contain scars. That matched observation. For a moment, confidence returned. Perhaps the chaos made sense. But there was another problem. Different simulations produced different halos. This was the second failure. Theoretical precision remained elusive. Change assumptions about dark matter properties, merger histories, baryonic feedback or satellite interactions, and outer halo predictions shifted significantly. Some models produced compact halos. Others extended much farther outward. Some suggested smoother distributions. Others predicted rich substructure. The galaxy remained ambiguous. Data alone was not enough. Interpretation mattered. Then observational missions pushed farther. Astronomers began identifying stars at truly extraordinary distances from the galactic center. Some appeared hundreds of thousands of light-years outward. Others belonged to streams from disrupted dwarf galaxies. Certain populations moved in ways suggesting recent mergers. Still others hinted at ancient accretion events whose remnants had not fully mixed into the halo. The edge kept retreating. Every time astronomers thought they were nearing the boundary, new structures appeared farther out. This created a strange psychological pattern. The galaxy expanded every time we improved measurement. The better humanity looked, the larger home became. And then came the satellite galaxy problem. Orbiting the Milky Way are dozens of dwarf galaxies, including companions like the Large Magellanic Cloud and Small Magellanic Cloud. These are not passive ornaments, they're gravitational actors. Their motion perturbs the Milky Way's disk. Their dark matter halos interact with ours. Their tidal influence can reshape outer structures. This mattered for a troubling reason. To estimate the Milky Way's total mass, astronomers often use satellite motions. But if satellite systems themselves are evolving dynamically, their trajectories become difficult to interpret cleanly. Recent infall events, tidal stripping, and transient interactions can bias mass estimates. In simpler terms, the measuring tools were moving. Imagine trying to determine the size of a whirlpool by tracking drifting leaves, only to realize wind also pushes the leaves unpredictably. Motion becomes harder to decode. That became the third failure. Even indirect gravitational probes introduced uncertainty. By now, the original dream of a clean galactic census was fading. The galaxy was not yielding a single coherent outer boundary. Instead, every mission revealed additional layers of structure. Visible stars, ancient halo populations, merger debris, satellite interactions, dark matter subhalos, warped gas disks. The Milky Way increasingly resembled a living ecosystem rather than a finished object. And ecosystems resist edges. A forest rarely ends at a line. Dense woodland becomes sparse woodland. Sparse woodland becomes grassland. Grassland becomes shrubland. Boundaries blur because systems overlap. Astronomers were beginning to suspect galaxies behave similarly. Then another anomaly appeared. Certain large-scale stellar structures did not fit known merger models or standard halo distributions. They appeared too organized to be random debris, too large to be local disturbances, and too strange to fit existing expectations. These structures were ghost-like, vast, diffuse, unexpected, and they suggested something even more unsettling. Perhaps the outer Milky Way was not merely messy. Perhaps entirely new classes of structure existed near the galactic frontier. The failed missions had done something unexpected. They had not found the edge. They had discovered stranger questions, and among the strangest were structures so faint and so vast that for years astronomers were not even sure they were real. Ghost structures. At the outer limits of the Milky Way, astronomy entered a realm where certainty began to dissolve. The structures now emerging from observational surveys were difficult to classify, difficult to model, and in some cases difficult even to believe. They were too large to dismiss as local anomalies, too faint to observe cleanly, and too strange to fit comfortably inside conventional galactic maps. They did not resemble neat spiral arms or compact globular clusters. They were diffuse, sprawling, and ghost-like. And perhaps most unsettling of all, they suggested the galaxy possessed hidden architecture beyond anything earlier generations imagined. One of the first major clues came from enormous stellar overdensities discovered in the outer disk and halo. These were regions where stars appeared more concentrated than expected, but not in ways matching known galactic structures. They were too extended to be ordinary clusters, too coherent to be random noise, too massive to ignore. Among the most famous was the Monoceros ring, a vast band of stars wrapping around the outer Milky Way like a ripple frozen in time. Its discovery created immediate controversy. What exactly was it? No one agreed. Some astronomers proposed it was the remnant of a dwarf galaxy torn apart by tidal forces, its stars stretched into a gigantic loop encircling the galaxy. Others argued it was not merger debris at all, but part of the Milky Way's own warped outer disk, distorted upward and downward by gravitational interactions. Still others suggested a hybrid explanation involving both disk oscillation and accretion. Each model explained part of the evidence. None explained everything. That uncertainty mattered because the interpretation changed the meaning of the structure itself. If the ring came from an external dwarf galaxy, it represented galactic cannibalism on an enormous scale. If it originated internally, it implied the Milky Way's disk could oscillate like a disturbed membrane, generating waves thousands of light-years high. Either explanation was extraordinary, and the Monoceros ring was only the beginning. As surveys improved, more ghost structures appeared. The Virgo crossover density revealed a massive excess of stars in the direction of the constellation Virgo. It extended over enormous regions of space and resisted easy classification. Was it a disrupted galaxy? A merger remnant, a halo asymmetry? Again, consensus proved elusive. Then came stellar streams on scales so vast they felt almost geological. Long ribbons of stars curved around the galaxy, some stretching tens of thousands of light-years. These streams preserved memory of destroyed systems, their stars still following related orbital paths, long after their original galaxies had ceased to exist. Astronomers began to think like archaeologists. The Milky Way was not merely a galaxy. It was a fossil record. Every ghost structure represented a past collision, an ancient infall, or a gravitational disturbance written into stellar motion. The outskirts had become historical archives. But there was a deeper problem. Ghost structures implied that the galaxy was not in equilibrium. For decades, many galactic models assumed the Milky Way was approximately stable, at least on large scales. Certainly, stars moved, gas flowed, and mergers occurred, but models often treated large structures as relatively settled over long timescales. The ghost structures challenged that assumption. The outer galaxy appeared restless, perturbed, still ringing from past encounters. Imagine striking a bell. The metal vibrates long after impact. Even if the strike lasted only a fraction of a second, waves continue propagating through the structure. In a similar way, galactic collisions may produce gravitational ripples that persist for billions of years. The Milky Way may still be vibrating from ancient encounters. That possibility transformed the meaning of the edge. An edge assumes a stable object. But what if the object is oscillating? What if the outer disk rises and falls like waves on water? What if stellar densities change over cosmic time as gravitational disturbances propagate outward? Then the boundary becomes not just diffuse, it becomes dynamic, a moving frontier. This idea gained support as astronomers observed vertical oscillations in stellar populations near the disk. Some stars appeared displaced above the galactic plane, others below. Large-scale wave patterns suggested something massive had disturbed the disk. One leading suspect was the Sagittarius dwarf spheroidal galaxy. This small satellite galaxy has been plunging through the Milky Way for billions of years, gradually being torn apart by tidal forces. Though tiny compared with the Milky Way, repeated passages through the galactic disk may have triggered massive gravitational disturbances. A dwarf galaxy, disturbing a giant. Scale can be deceptive in gravity. A pebble dropped into a lake can generate ripples across the entire surface. If Sagittarius triggered oscillations across the outer disk, then some ghost structures may not be external debris at all. They may be internal waves. The galaxy may be ringing. This realization created a profound conceptual shift. Astronomers had spent decades searching for fixed structures to define the galactic edge. But fixed structures were becoming rare. Outer regions behaved less like architecture and more like weather. Weather does not have edges. Storms expand, weaken, merge, and reorganize. Boundaries fluctuate. The Milky Way's outskirts increasingly resembled atmospheric dynamics on cosmic scales. Yet one final mystery remained. Some ghost structures appeared too large to explain through visible interactions alone. Their motions hinted at perturbations from unseen mass concentrations, invisible gravitational actors, dark substructures. This possibility emerged directly from cosmological dark matter simulations. If dark matter forms hierarchical halos, then the Milky Way should contain not only one large halo but many smaller sub-halos embedded within it. most may contain little visible matter. They could pass through the outer galaxy almost unseen. Almost. Not entirely. Even invisible mass leaves fingerprints. As dark subhalos move through stellar streams, they can distort trajectories, carve gaps, and create subtle gravitational scars. In principle, these disturbances allow astronomers to detect invisible structures indirectly. This was an astonishing development. Ghost structures were now being used to search for invisible ghosts. Visible stellar streams could reveal dark matter subhalos that emitted no light whatsoever. The galaxy had become layered mystery upon mystery. Visible stars tracing invisible structures, ancient debris revealing hidden mass, outer ripples preserving collisions billions of years old. By now one conclusion was unavoidable. The Milky Way was far stranger than the smooth spiral diagrams in textbooks suggested. Its edge was not clean, not static, not even fully luminous. And yet amid all this complexity, a few scientists had seen the deeper truth decades earlier. Long before modern sky surveys, long before massive computational simulations, long before dark matter became mainstream. One astronomer in particular had issued a warning the scientific world would spend decades learning to understand. Her measurements showed that something fundamental about galaxies was deeply wrong. Her name was Vera Rubin, and the story was about to become personal. In science, some discoveries arrive like explosions. Others arrive quietly. No dramatic flash. No immediate revolution, no instant consensus. Just careful measurements, repeated observations and results so persistent that reality slowly forces the scientific world to change. The work of Vera Rubin belongs to the second category. Her warning was not loud, it was precise. And it changed how humanity understood every spiral galaxy, including the Milky Way. Rubin was born in 1928 in Philadelphia, and grew up during a period when professional astronomy remained heavily restricted for women. Even entering the field required persistence. Access to observatories, research positions, and academic opportunities was often limited by assumptions that had little to do with scientific ability. Yet Rubin persisted, driven by something stronger than institutional resistance. Curiosity. From an early age, she was fascinated by motion in the sky. Not just stars as points of light, but systems in motion, patterns, rotations, relationships between massive objects separated by vast distances. That focus on motion would prove decisive, because motion tells truth when appearance misleads. By the mid-20th century, astronomers had already accumulated hints that galaxies contained missing mass. The problem was not entirely new. In the 1930s, Fritz Zwicky studied galaxy clusters and concluded that visible matter could not explain observed motions. He proposed the presence of unseen mass, which he called Dunkel Materie dark matter. His conclusion was radical and largely ignored. Part of the reason was evidentiary. Zwicky worked with galaxy clusters, enormous systems with complex dynamics and significant uncertainty. His calculations were provocative, but easy for skeptics to challenge. The anomaly remained interesting, not definitive. Rubin's work changed that. Instead of studying entire clusters, she focused on spiral galaxies' cleaner systems, whose rotational behavior could be measured with increasing precision. Working closely with astronomer Kent Ford Rubin, used highly sensitive spectroscopic instruments to measure stellar velocities at different radii from galactic centers. The method depended on the Doppler effect. Stars moving toward us shift light slightly. Stars moving away shift differently. Measure these shifts carefully across a galaxy and rotational speed can be reconstructed. This sounds technical. Its consequence was philosophical, because galaxies began speaking through motion, and what they said was troubling. Rubin expected at least broadly what classical gravitational theory predicted. Inner regions should rotate quickly because they contain dense concentrations of visible matter. Outer regions where stars become sparse should slow down. Instead, the rotation curves flattened. Not once, repeatedly. Galaxy after galaxy. The outer stars refused to slow. Pause and imagine the emotional weight of that result. Scientific revolutions rarely happen in one moment. More often they emerge through repetition. The first anomaly invites skepticism. The second raises interest. The 10th forces reconsideration. Rubin's power lay not in discovering one strange galaxy, but in revealing a pattern too consistent to dismiss. Something fundamental was wrong with prevailing models, and the implications were enormous. If outer stars moved this fast without flying away, something massive had to be holding them in orbit. That mass was not visible in stars' gas or dust. It surrounded galaxies invisibly yet dominated their gravitational structure. Visible galaxies were incomplete. This conclusion transformed the Milky Way overnight. For centuries, humanity had imagined galaxies as luminous systems defined primarily by stars. Rubin's work suggested the opposite. Stars might be secondary. The true galactic structure might be mostly invisible. Think about how radical that sounds. Imagine learning that the visible part of a city, the roads, buildings, lights, and people, accounts for only a small fraction of its true structure. Beneath everything lies a massive, unseen foundation, controlling flow, stability, and shape. The visible city becomes surface expression. Rubin implied galaxies behave similarly. The glowing spiral arms that dominate astronomical imagery may be surface phenomena embedded within vastly larger dark halos. For the search for the galactic edge, this was devastating. Before Rubin, the problem was observational. After Rubin, the problem became conceptual. What exactly are we measuring? The visible edge of stars, the edge of ordinary matter, or the outer limit of the dark halo controlling galactic gravity? Each answer produced a different galaxy. This changed the central question. Where does the Milky Way end? Now depended on what one means by Milky Way. If the Milky Way means luminous stars, the edge lies at one scale. If it means gravitational dominance, the edge may lie hundreds of thousands of light years farther outward. If it includes all bound dark matter, the scale grows larger still. The galaxy expanded because definition changed. Rubin understood something deeper than many of her contemporaries. The real significance of dark matter was not merely that mass was missing. It was that human intuition had been built around visible structure. We instinctively trust what shines. Galactic dynamics forced a humbling correction. Visibility is not importance. The brightest structures are not always the dominant ones. This principle extends beyond astronomy. Civilizations often organize around visible power while hidden systems do the real work. Infrastructure, logistics, supply chains, social trust, and energy networks rarely attract attention until failure reveals dependence. Galaxies, it seemed, obeyed a similar logic. The visible disk is dramatic. The invisible halo governs structure. Rubin's warning reached beyond astrophysics. It challenged perception itself. By the 1980s and 1990s, dark matter had become central to cosmology. Simulations of galaxy formation increasingly required dark halos to explain observed large-scale structure. The Milky Way was no exception. Its visible spiral form could no longer be interpreted independently of the hidden mass surrounding it. Yet one obstacle remained. Rubin proved missing mass existed. She didn't reveal the precise shape of the Milky Way's dark halo. That task would require something more ambitious than any previous astronomical mission. Humanity needed not just velocity measurements. It needed a three-dimensional map of stellar motion across the galaxy. Not thousands of stars. Not millions. Billions. The scale of data required bordered on absurd. And yet decades after Rubin's warning, technology finally approached that threshold. The next breakthrough would come from space. From a mission designed to do something humanity had never achieved before. Map our galaxy with such precision that invisible structure could be reconstructed from motion itself. The mission had a simple name, Gaia, and it would redraw the Milky Way. Long before space missions could map billions of stars, one astronomer had already begun to suspect that the edge of the galaxy was not where the light ended. In the mid-20th century, working in the Netherlands, Jan Oort approached the Milky Way with a different kind of question. Not where does it end in light, but how far does its gravitational influence truly extend? At first, this seems like a subtle shift in perspective. In reality, it is a complete transformation of the problem. Light draws a picture. Gravity defines reality. Oort studied stellar motions near the solar neighbourhood, trying to understand how stars move relative to the galactic centre. He was among the first to formalise the idea that the Milky Way rotates as a system with stars orbiting within a massive disk-like structure. But his deeper insight came when he considered not just the visible disk, but the surrounding environment of faint stars and globular clusters. He began to suspect something extraordinary. The galaxy might not have a sharp gravitational boundary at all. Instead, it could be surrounded by a vast reservoir of distant objects still weakly bound to its gravity, even at extreme distances. This idea led to the concept of what would later be called the Oort cloud in solar system studies, but on galactic scales, the implications were far more unsettling. If the solar system can possess a distant shell of icy bodies extending tens of thousands of astronomical units from the Sun, then perhaps the Milky Way possesses a similar extended structure on incomparably larger scales. A gravitational atmosphere. Not visible, not luminous, but real. Oort's thinking hinted at something critical. The galaxy might not end where stars stop being common. It might end where gravitational binding finally fails. But even that definition hides complexity, because gravity does not fail abruptly. It weakens, gradually extending influence far beyond visible matter. The outer regions of the Milky Way may still gently tug on objects at distances so large that orbital periods exceed billions of years. Time itself becomes part of the boundary problem. If something takes longer than the age of the universe to complete one orbit, is it still part of the galaxy? There is no easy answer. This is where Oort's insight becomes unsettling. He understood that the galaxy is not a simple object with a defined edge. It is a dynamical system embedded in a larger gravitational environment. The Milky Way interacts continuously with nearby structures, exchanging material energy and momentum. Even the concept of belonging becomes ambiguous. Does a star belong to the Milky Way if it is only loosely bound? What about a star passing through the outer halo on a long elliptical orbit? What about matter being slowly stripped away by tidal forces? The farther one pushes outward, the more membership becomes probabilistic rather than absolute. And then came a deeper realization. The Milky Way is not isolated. It is part of a larger gravitational community known as the local group. Within this group, the dominant actors are the Milky Way and the massive Andromeda galaxy. These two galaxies are not static neighbours. They're moving toward each other at high velocity, bound by mutual gravity, destined for a slow cosmic encounter over billions of years. This motion complicates everything, because the outer regions of each galaxy are already interacting. Their halos overlap, their gravitational fields interpenetrate. Their satellite systems are influenced by both. In such an environment, defining a clean edge becomes almost meaningless. The space between galaxies is not empty. It is filled with low-density gas-stray stars, dark matter filaments, and overlapping gravitational influence zones. Oort's invisible frontier was not a line. It was a region of gradual transition, a zone where the identity of Milky Way becomes less certain. This idea leads directly to a conceptual breakdown. If galaxies overlap in influence, then the universe is not composed of isolated islands. It is composed of interconnected gravitational fields. That means the Milky Way's edge is not just hard to find. It may not exist in the way we intuitively imagine. And yet astronomers still needed practical definitions. Observations required boundaries. Models required limits. Even if reality was continuous, science needed operational edges to measure mass motion and structure. So astronomers adopted a compromise. Define the galaxy by gravitational dominance. Where the Milky Way's gravity is stronger than external gravitational fields, we consider matter part of the galaxy. Where external forces dominate, we consider matter intergalactic. This definition is useful, but it hides a deeper truth. Because gravitational dominance shifts over time. As the Milky Way and Andromeda approach each other, their gravitational territories are already changing shape. The boundary between them is not fixed. It moves as mass redistributes and trajectories evolve. Oort's invisible frontier is therefore not just spatial, it is temporal. The edge of the galaxy depends on time as much as position, and that leads to a profound consequence. If the boundary is changing, then any snapshot of the Milky Way is incomplete by definition. We are not observing a finished object. We are observing a moment in an ongoing gravitational process. This insight sets the stage for the next revolution, because while Oort and his successors were redefining the galaxy conceptually, technology was preparing to do something no human had ever done before: measure the motion of stars across the entire sky with unprecedented precision, not in fragments, not in selected regions, but as a complete dynamical map of the galaxy itself, a machine capable of turning motion into structure, a satellite designed to reveal not just where stars are, but how they move through the invisible architecture of space, and with that motion reveal the shape of the unseen Milky Way, a mission that would finally begin to show whether Oort's invisible frontier was a boundary, or a mirage. When the mission of Gaia was conceived under the direction of the European Space Agency, it was not designed to answer a poetic question about the edge of the Milky Way. It was designed to measure, precisely, relentlessly, systematically. Its purpose was to chart the position, distances and motions of over 1 billion stars. Not in isolated patches of sky, not in targeted surveys of interesting regions, but across the entire celestial sphere, constructing a 3-dimensional map of unprecedented detail. Yet beneath the technical ambition, something deeper was happening. For the first time in human history, the galaxy would not be inferred from fragments. It would be reconstructed from motion itself. Gaia does not simply observe stars as points of light. It tracks their subtle shifts against the background sky, measuring parallax proper motion and velocity with extraordinary precision. Over time, these tiny movements accumulate into a dynamic portrait of the galaxy as a living structure, and what emerged from early data releases was not a static Milky Way. It was a system in motion, a system in tension, a system still assembling itself. The first shock came from scale. The stellar disk was larger than many previous models suggested. Structures extended farther outward. Spiral arms appeared more complex, less symmetric, more fragmented. The galaxy was not a clean spiral drawn in ink. It was a layered, evolving pattern shaped by gravitational history. Then came the second shock. The motion of stars revealed waves, not random motion, not uniform rotation, but coherent ripples propagating through the galactic disk. Some regions of stars were moving upward above the galactic plane. Others were moving downward below it. These oscillations suggested the disk itself had been disturbed in the past and was still responding. The Milky Way was not calm. It was ringing like a struck bell. This idea immediately connected back to earlier suspicions. If the galaxy is still oscillating, then it has not reached equilibrium. And if it has not reached equilibrium, then any attempt to define a stable edge becomes inherently approximate. Gaia's data made this clearer than ever. The outer galaxy is not static enough to possess a clean boundary, but the most transformative insight came from mapping stellar streams and halo structure in detail. Gaia revealed that the galactic halo is richly structured, filled with remnants of ancient mergers and ongoing accretion events. Entire dwarf galaxies have been torn apart and stretched into long filaments of stars wrapping around the Milky Way. These streams preserve orbital memory, allowing astronomers to reconstruct past gravitational interactions like forensic evidence. One of the most important realizations was that the Milky Way is still actively growing. It is not a completed structure. It is still consuming smaller systems. Stars continue to fall inward from satellite galaxies. Dark matter substructures continue to merge and reorganize. Gas continues to accrete along cosmic filaments. The galaxy is a dynamic system still assembling its outer layers. This raises a crucial implication. If the Milky Way is still growing, then its edge is not a fixed location. It is a moving frontier defined by ongoing accretion. Gaia also refined the understanding of the galactic warp and flare. The outer disk is not simply bent, it is dynamically shaped by gravitational interactions with satellite galaxies such as the Large Magellanic Cloud and Small Magellanic Cloud. The gravitational influence is strong enough to distort the Milky Way's outer structure over time. This means the galaxy's outskirts are not passive. They are reactive. They respond continuously to external forces, and that response propagates inward. What appears as an edge is actually a zone of interaction between internal structure and external gravitational fields. Gaia's data also sharpened estimates of the Milky Way's total mass. The visible disk remains only a small fraction of the full gravitational system. The dark matter halo extends far beyond the luminous components dominating the galaxy's total mass budget and shaping its long-term evolution. Yet even Gaia could not define a single boundary. Instead, it revealed layers: a bright inner disk, a thicker stellar disk, a vast halo of ancient stars, a diffuse dark matter halo extending even farther, and beyond that gravitational influence merging with the broader environment of the local group, where the Milky Way and the Andromeda Galaxy slowly approach each other across intergalactic space. Each layer fades into the next. No hard cut-off appears, only transitions. This is the key transformation Gaia delivers. The Milky Way is no longer a static object with a boundary waiting to be discovered. It is a multi-layered gravitational system embedded in a larger cosmic web, and its edge is not a line. It is a gradient of influence, a region where different forces compete. Inside that region, identity becomes uncertain. Is a star at the far halo still part of the Milky Way if Andromeda's gravity begins to influence it as strongly? Is matter still galactic if it participates in multiple gravitational systems at once? Gaia does not answer these questions directly, but it forces them into clarity. Because what it reveals is that the galaxy is not defined by what it contains. It is defined by what it influences, and influence does not end cleanly. It fades. It overlaps. It shifts over time. This is where the search reaches a turning point. For centuries, humanity looked for the edge of the Milky Way as if it were a place. Gaia suggests it is not a place at all. It is a condition, and conditions do not have borders. They have transitions. This realization leads directly into the next phase of the story. Because if the galaxy is defined by influence rather than structure, then the true question is no longer where the Milky Way ends. It is how far its influence extends into the surrounding universe. And that answer will take us beyond the galaxy itself, into the space between galaxies, where the concept of edge begins to dissolve entirely. For centuries, humanity imagined the edge of the Milky Way as something waiting to be found, like a shoreline hidden in fog. Something fixed, something external, something that existed independently of the observer. But as measurements improved, especially through missions like Gaia under the European Space Agency, a more unsettling picture emerged. The edge was not waiting, it was changing. The first hint came from stellar motion in the outer disk. Stars did not move as if confined inside a rigid finished structure. They moved as if embedded in a system still reacting to past disturbances. Ripples propagated through the disk. Vertical oscillations rose and fell across vast regions. Orbital patterns carried signatures of ancient interactions that had not yet settled. A galaxy in equilibrium would look quiet on large scales. The Milky Way did not. Then the halo deepened the mystery further. Gaia's precision revealed that the outer stellar halo is not a smooth spherical shell. It is a patchwork of substructures streams over densities remnants of dwarf galaxies and diffuse stellar populations with distinct orbital histories. Some of these structures are recent, others are ancient beyond easy classification. The halo is still assembling. That means the outer boundary of the galaxy is not simply expanding into space. It is being actively constructed over time. New material arrives. Old material is redistributed. Some structures are absorbed. Others are torn apart and stretched across hundreds of thousands of light years. The Milky Way is not just rotating. It is growing. And growth implies movement at the boundary. But the most important realization came when astronomers began to combine stellar motion data with models of the dark matter halo. The dark matter structure surrounding the galaxy is not static. It responds dynamically to mergers, satellite interactions, and internal rearrangements. As the Milky Way interacts with nearby dwarf galaxies such as the Large Magellanic Cloud and Small Magellanic Cloud, gravitational perturbations ripple through both visible and invisible matter. This produces a profound consequence. The outer gravitational boundary of the galaxy is not fixed in space. It shifts in response to interactions. Imagine drawing a circle in water. The moment you try to define its edge, ripples distort the shape. Now imagine that water is itself moving through a larger current while interacting with other currents, while being influenced by unseen forces beneath the surface. That is the Milky Way's boundary, not a line, a constantly evolving distortion. Then comes a deeper layer of movement. The Milky Way does not exist alone. It resides within the local group, a gravitationally bound system that includes the massive Andromeda galaxy. These two galaxies are not static neighbours. They're moving toward one another at high velocity, locked in a gravitational trajectory that will unfold over billions of years. This motion changes everything about the outer galaxy, because gravity does not belong to a single object. It is shared across space. As Andromeda approaches, its gravitational influence begins to subtly reshape the outer regions of the Milky Way. Far beyond the visible disk, the gravitational fields of both galaxies begin to overlap. In these regions, matter does not clearly belong to one system or the other. It is influenced by both. This creates a zone of gravitational ambiguity, a region where identity is not defined by location but by competing forces. In such a region, the concept of a fixed edge becomes increasingly fragile. The Milky Way's boundary is not just moving inward or outward. It is being pulled in multiple directions at once. And over cosmic time, this boundary will not simply shift. It will dissolve. Because in a future where galaxies merge, the idea of separate edges becomes meaningless. The Milky Way and Andromeda will eventually form a single gravitational system redistributing stars, gas and dark matter into a new configuration. What then was the edge of the Milky Way at that moment? A temporary shape, a phase in a longer transformation. Gaia's data makes this unavoidable. The galaxy is not a static object with a defined perimeter. It is a process unfolding across billions of years. Every edge we define is simply a snapshot of that process at a particular time. This realization forces a shift in perspective. We stop asking where the Milky Way ends in space. We begin asking where it ends in time. Because if structure is continuously evolving, then boundaries are not spatial absolutes. They are temporal moments. And that leads to a deeper implication. The galaxy we observe is already outdated. The light we receive from its outer regions left tens of thousands of years ago. The motion we measure reflects past states. The structure we reconstruct is always slightly behind reality. We are not seeing the Milky Way as it is. We are seeing the Milky Way as it was, and in a system that is actively evolving, that difference matters. The edge we map today may already have shifted by the time the data reaches full interpretation. This creates a subtle but important instability in the entire concept of a galactic boundary. Even with perfect instruments, the edge would not remain fixed, because the system itself is not fixed. This is where the narrative turns inward again. The galaxy is not only changing externally, it is changing in how it can be understood. As data improves, definitions shift. As models evolve, boundaries move. As simulations refine structure, previous edges dissolve into new layers. The edge of the Milky Way is not simply a physical problem. It is a moving target shaped by knowledge itself. And that leads to a final realization. Perhaps the edge was never meant to be found as a line. Perhaps it was always a process of continual redefinition, a horizon that moves as understanding deepens. And if that is true, then the search for the edge is not a search for a place. It is a search for perspective, a way of seeing the galaxy that accepts motion, overlap, and transformation as fundamental. In that sense, Gaia did not give us a final answer. It gave us something more unsettling. It showed us that the question itself evolves. And with this time, the Milky Way expands not in size alone, but in meaning. By the time humanity reached the most precise maps of the Milky Way ever constructed, a quiet contradiction had settled into the data. The visible galaxy looked finite. The gravitational galaxy refused to be finite. This tension defined everything that followed. At the centre, the luminous disk of the Milky Way appeared familiar spiral arms, star-forming regions, clusters of young blue stars tracing elegant arcs through space. But as observations extended outward, the structure did not simply fade, it transformed. First into a thicker stellar disk, then into a diffuse halo of ancient stars, then into something far larger, far more elusive, a hidden gravitational structure that did not shine at all. This was the dark matter halo. It cannot be seen directly. It reveals itself only through motion, through the bending of trajectories, through the way stars refuse to obey the expectations of visible mass alone. And yet, despite its invisibility, it dominates the galaxy. The visible Milky Way is only the bright core of a far larger system embedded inside this halo. Estimates suggest the dark component extends hundreds of thousands of light years beyond the luminous disk, possibly approaching scales of 1,000,000 light-years in radius, depending on definition and model. At this scale, the galaxy stops resembling a neat spiral and begins resembling something else entirely. A gravitational atmosphere. Not solid, not bounded, but pervasive. To understand what this means, imagine a mountain range submerged beneath fog. The peaks are visible, the valleys can be mapped where fog thins, but the fog itself extends far beyond what the peaks suggest, filling space, in ways that define the entire environment without revealing its structure. The dark matter halo behaves like that fog, except it is not atmospheric, it is gravitational. It does not block light, it shapes motion. And within this invisible structure, the visible galaxy is only the most concentrated region of activity. The implication for the galactic edge are immediate and unsettling. If the dominant mass of the Milky Way exists in a diffuse halo, then there is no obvious point where the galaxy stops being itself. Instead, density gradually decreases with distance. Gravitational influence weakens but never drops abruptly. There is no clean cut-off, only diminishing effect. The halo does not end, it fades. This fading is crucial, because a fading structure cannot have a sharp boundary without an arbitrary definition. Astronomers can choose a radius where density drops below a certain threshold. They can define a virial radius where gravitational binding becomes statistically significant. They can adopt conventions for practical measurement, but nature does not choose those conventions. It simply continues. And as observations improved, the halo revealed even more complexity. It is not smooth. It contains substructure. Dark matter subhalos predicted by cosmological models may orbit within the main halo like invisible satellites. These substructures can perturb stellar streams, carve gaps into them, and subtly distort orbital paths of visible matter. The outer galaxy becomes a field of interaction between luminous debris and invisible gravitational architecture. The Milky Way is no longer a single object. It is a hierarchy, a nested system of structures within structures, stars inside clusters, clusters inside a disk inside a stellar halo inside a dark matter halo, and that halo itself embedded in a larger cosmic environment. Each layer fades into the next. Each boundary becomes less distinct. Then comes the most disorienting realization. The dark halo is not isolated. It is part of the cosmic web. Filaments of dark matter stretch across intergalactic space, connecting galaxies in vast networks. The Milky Way is not a solitary island in emptiness. It is a node in a larger structure linked to other galaxies through invisible scaffolding. This means that even at extreme distances, the concept of outside becomes ambiguous. Outside what? Outside the visible disk, outside the stellar halo, outside the dark matter halo, outside the local group. Each answer expands the scale. Each expansion dissolves the boundary further. And still the question remains. Where does it end? The hidden halo forces a new interpretation of the galaxy's edge. It is not a perimeter. It is a gradient of decreasing gravitational dominance embedded in a larger network of competing gravitational fields. Even the idea of escape becomes complicated. To leave the Milky Way is not simply to cross a line. It is to gradually move from one gravitational regime into another, while still being influenced by multiple overlapping structures. A spacecraft drifting outward would not suddenly exit the galaxy. It would slowly lose definition of what it means to be inside it. At some distance, it might still be weakly bound. At greater distances, it might be influenced more by external galaxies than by its origin. But there is no moment of separation, only transition. This is the central shift the hidden halo imposes. Boundaries are replaced by influence fields, edges are replaced by gradients, and identity becomes dependent on context. This raises a deeper question that begins to shape the next stage of the story. If the Milky Way has no sharp boundary in matter or gravity, then what exactly are we trying to define when we search for its edge? Are we mapping structure, or are we trying to impose structure onto something that fundamentally resists it? The hidden halo does not answer. It expands the uncertainty, and in doing so it pushes the story beyond astronomy and into something more fundamental, the nature of belonging itself. There is a point in every attempt to define the edge of the Milky Way where the idea of outside begins to fail. It does not fail suddenly. It fails gradually as overlapping gravitational influences blur what once seemed like clear separation. This is the collision zone, a region of space where galaxies do not end but intersect. For most of human history, galaxies were imagined as isolated islands in a vast cosmic ocean. The image was powerful because it was simple. Each galaxy was a self-contained system drifting alone through emptiness separated from others by incomprehensible distances. But that image is incomplete. The Milky Way exists inside a gravitational neighborhood known as the local group. Within this region, galaxies are not isolated. They're dynamically connected, exchanging influence across millions of light years. The most important partner in this system is the massive Andromeda galaxy. For billions of years, Andromeda and the Milky Way have been moving toward each other, not in a straight line like colliding objects in everyday space, but through a complex gravitational trajectory shaped by the total mass of the local group, including dark matter halos that envelop both galaxies and the space between them. At extreme distances from each galaxy, the distinction between belonging to one system or the other becomes increasingly ambiguous. A star in the outer halo of the Milky Way is not fully isolated from Andromeda's gravity. Andromeda is not fully isolated from the Milky Way's. Their gravitational fields overlap. Their dark matter halos interpenetrate. Their outer structures begin to respond to each other's presence long before any visible collision occurs. This is the collision zone. Not a point of impact, but a vast region of mutual influence. Inside this region, matter behaves differently. Stars in the outer reaches do not orbit a single dominant center with perfect clarity. Instead, their trajectories are shaped by competing gravitational pulls. Over cosmic time, these influences reshape orbits, distort halos, and subtly reconfigure the outer structure of both galaxies. In such an environment, the idea of a fixed galactic edge becomes increasingly fragile, because an edge implies separation, but the collision zone is defined by interaction. Consider what this means in practical terms. If a star lies far enough from the Milky Way's center, its motion may be influenced almost as much by Andromeda as by its original galaxy. In that regime, the question which galaxy does this star belong to becomes less meaningful. The answer depends on time trajectory and gravitational context, not on location alone. This is where the concept of galactic ownership begins to dissolve. Astronomers can define membership statistically by binding energy or orbital parameters, but those definitions are conventions imposed on a system that does not naturally divide itself cleanly. The universe does not label its structures. It only evolves them, and the collision zone is a consequence of that evolution. It represents a region where two enormous gravitational systems are already beginning to reshape one another long before any visible merger occurs. Over billions of years, this process will intensify. Stars will be redistributed. Dark matter halos will overlap more deeply. The current shapes of both galaxies will be transformed into a single merged system. But even before that final merger, the boundary between them is already unstable. This creates a profound implication for the search for the edge. If the Milky Way and Andromeda share a region of overlapping influence, then the outer boundary of each galaxy is not independent. It is codetermined. The edge of one depends on the existence of the other, and that dependence extends further outward into the broader structure of the local group itself, where smaller galaxies orbit within shared gravitational fields and diffuse matter connects systems across vast distances. The collision zone is therefore not just between two galaxies. It is between definitions, between identities, between ways of thinking about structure. Inside this zone, the universe behaves less like a collection of isolated objects and more like a continuous gravitational field with localized concentrations. The Milky Way is one such concentration, and its edge is not a barrier separating it from emptiness. It is a region where its influence competes with other influences. This reframes the entire problem. Instead of asking where the galaxy ends, we are forced to ask where its influence becomes weaker than that of surrounding structures. But even that question is unstable, because influence itself depends on scale. At small scales, the Milky Way dominates nearby stars. At larger scales, Andromeda competes. At even larger scales, the entire local group behaves as a single gravitational system embedded in the cosmic web. So the boundary shifts depending on what level of structure one chooses to examine. This is the deeper lesson of the collision zone. There is no single correct scale for defining a galaxy, only nested scales of interaction, each with its own edge, each dissolving into the next. And as astronomers map these overlapping regions with increasing precision, one conclusion becomes unavoidable. The Milky Way is not an isolated entity. It is part of a continuous gravitational landscape where separation is approximate, not absolute. But even this realization is not the final stage of the story. Because if galaxies are not isolated islands, then the next question becomes even more unsettling. What happens when the very idea of a galaxy as a distinct object begins to break down entirely? That is where the narrative must now go, into regions where structure itself becomes uncertain, and where the meaning of belonging to a galaxy begins to disappear. At a certain point in the study of the Milky Way, the question stops being about edges and starts becoming about categories. What exactly is a galaxy if its boundaries are not sharp? For centuries, the answer seemed obvious. A galaxy was a gravitationally bound system of stars, gas dust, and whatever invisible structure held them together. It was a unit, a structure, a thing. But as observations extended outward, that definition began to strain. The first cracks appeared in the outer halo where stellar streams from disrupted dwarf galaxies wrap around the Milky Way in vast arcs. These streams are not part of the disk, yet they are not fully separate either. They are debris still gravitationally responding to the Milky Way while retaining memory of their origin. Then came the realization that the halo itself is not isolated. It extends into a broader environment shaped by the local group where the Milky Way coexists with the massive Andromeda galaxy and dozens of smaller companions. Within this region, matter is not cleanly partitioned. Gravitational influence overlaps. Dark matter distributions interpenetrate. Gas filaments stretch between systems. The space between galaxies is not empty. It is structured. This is where the blurring begins. On extremely large scales, galaxies are not isolated points. They sit along filaments of the cosmic web connected by tenuous threads of gas and dark matter. These filaments guide motion-feed galaxies and shape large-scale structure across the universe. In this view, the Milky Way is not a standalone object. It is a node within a continuous network, and nodes do not have edges in the traditional sense. They have gradients of density. As one moves outward from the Milky Way's center, matter becomes less concentrated, but never abruptly disappears. Stars thin into the halo. The halo fades into dark matter-dominated regions. Those regions merge into the larger gravitational environment of the local group. Beyond that lies intergalactic space. But even that space contains diffuse gas and dark matter structures linking galaxies together. At no point does structure fully cease. It only changes character. This creates a conceptual problem that grows sharper the more precisely we observe it. If galaxies exist within a continuous cosmic web, then the idea of a discrete galaxy becomes an approximation rather than a fundamental object. This doesn't mean galaxies are illusions. It means their boundaries are emergent. They arise from how matter clusters, not from a natural separation in space. That distinction is crucial because emergent boundaries depend on scale. Zoom in and structure appears fragmented and complex. Zoom out and patterns smooth into continuous fields. The Milky Way's edge changes depending on the level of resolution used to observe it. This is why different measurement methods produce different answers. Stellar distributions suggest one boundary. Gas distributions suggest another. Dark matter simulations suggest a far larger one. Gravitational influence suggests no clear boundary at all. Each method is correct within its own framework, but no single framework is complete. The galaxy resists unification under a single edge because it exists across multiple interacting layers of structure. And as astronomers pushed further into the outer regions, even the distinction between the Milky Way and neighbouring systems began to blur. The outskirts of Andromeda and the Milky Way are not sharply separated in gravitational terms. The halos extend toward one another, and over cosmic time their interactions reshape both systems. At extreme distances, matter is influenced by both galaxies, simultaneously making strict assignment difficult. Is a distant star part of the Milky Way if it responds to Andromeda's gravity almost equally? Is a gas cloud part of either galaxy if it participates in the shared environment of the local group? These are not rhetorical questions. They are operational uncertainties, and they matter because they reveal something deeper about cosmic structure. The universe does not organize itself into clean categories. It organizes itself into fields of influence. Within those fields, objects emerge as regions of higher density, not as isolated entities. This perspective transforms the search for the galactic edge into something more abstract. We are no longer looking for a boundary line. We are looking for a threshold of dominance. Where does the Milky Way's influence become less significant than surrounding structures? But even that threshold is unstable, because influence depends on time. As galaxies move, merge and interact, their gravitational fields evolve. What is outer Milky Way today may become intergalactic space in the future, or be absorbed into Andromeda during the eventual merger. The identity of a region is therefore not fixed, it is temporal. And this temporal nature of structure introduces a final layer of complexity. We're observing not a static object, but a phase in a long evolutionary process spanning billions of years. The Milky Way we map today is a snapshot of a system still forming, still interacting, still exchanging material with its surroundings. In that sense, every edge we draw is provisional, a temporary interpretation of a continuous process. This is why galaxies begin to blur together conceptually. Not because they physically merge everywhere at once, but because the rules used to separate them lose clarity at large scales. The further we extend our view, the more the universe resembles a continuous gravitational fabric rather than a collection of isolated islands. And in that fabric, the Milky Way is just one region of enhanced structure among many. This realization does not diminish the galaxy. It recontextualizes it. It shows that what we call a galaxy is a pattern of concentration within a larger continuum, a temporary stability in an evolving field. And once that is understood, the question of the edge begins to lose its original meaning entirely, because there is nothing to stand against. No empty void defining separation, only gradual transitions between regions of different density and influence. The Milky Way does not end where something else begins. It fades into everything else. And that fading sets the stage for the next shift in perspective. Because if galaxies are not isolated objects, then the final question is no longer about structure at all. It becomes about definition itself. What does it mean to say something belongs to a galaxy, when galaxies themselves are only patterns within a larger cosmic continuity? By this stage of the investigation, the word edge had begun to lose its authority. It no longer described a place. It described a choice, a way of interpreting the Milky Way that depended entirely on what one decided to measure and at what scale. Astronomers did not arrive at this realization through philosophy. They arrived through exhaustion. Every attempt to locate a physical boundary had produced a different answer. Stellar maps ended too early. Gas distributions extended farther. Dark matter halos stretched farther still. Gravitational influence blurred into the environment of the local group. where the Milky Way and the Andromeda Galaxy already share overlapping regions of influence. No single method produced a final perimeter. Instead, each method produced a different Milky Way. And so the question changed shape. Not where is the edge, but what do we mean by edge in the first place? The first modern attempt at a new definition came from gravitational physics. If a galaxy cannot be defined by visible light, then perhaps it can be defined by gravitational dominance. In this view, the Milky Way is the region of space where its gravitational influence is stronger than competing external forces. This definition is elegant, but it is unstable, because gravitational dominance is not absolute. It depends on distance, time, and surrounding structure. At one scale, the Milky Way dominates nearby stars. At another, Andromeda exerts comparable influence. At larger scales, the local group behaves as a single gravitational system embedded within the cosmic web. There is no single radius where dominance simply stops. It fades. This leads to a second attempt, the virial boundary. In astrophysics, a virial radius is used to define the approximate region within which a galaxy is gravitationally relaxed and bound. Beyond this radius, matter is less tightly bound and more influenced by external forces. It is a practical tool useful for simulations and modelling, but it is not a physical wall. It is a statistical threshold, a convention. Change the definition slightly and the boundary shifts. This is where the discomfort begins to grow. Because if the edge depends on definition, then the galaxy has no intrinsic perimeter, only interpretive ones. Then comes a third approach rooted in observation rather than theory. Define the galaxy by its luminous extent. Where stars become too sparse to detect the galaxy ends, this definition feels intuitive. It is also misleading, because detection limits are not physical limits. They are technological constraints. As instruments improve, the apparent boundary expands. Stars once considered too faint to matter become measurable. Structures once invisible become detectable. Each improvement pushes the edge outward. The boundary moves with the observer. This leaves a final option: define the galaxy by its constituents. Everything gravitationally bound to the Milky Way is part of it, but even this breaks down under deeper scrutiny, because binding is not binary. It is a spectrum. Some objects are tightly bound, orbiting predictably within the disk. Others are loosely bound, drifting through the halo on long, unstable trajectories. Still others are only marginally associated, influenced by both the Milky Way and external structures within the local group. And in the far outer regions, the distinction between bound and unbound becomes probabilistic. Not yes or no, but degrees of likelihood. At this point, the concept of a sharp edge is fully dissolved. What remains is a layered reality, a structure defined not by borders but by influence strength. Strong influence near the centre, weaker influence outward, competing influences in the outer halo, overlapping influences in intergalactic space. The Milky Way becomes a gradient field rather than an object with a perimeter. This is the new definition that slowly emerges from decades of accumulated evidence. A galaxy is not something that ends. It is something that fades. This fading is not a failure of measurement. It is a feature of cosmic structure, because the universe itself does not appear to be organized into isolated units. It is organized into continuous fields of matter shaped by gravity, dark matter, and cosmic expansion. Within that continuity, galaxies form as regions of enhanced density and stability. But regions do not require edges. They require gradients, and gradients are inherently soft. This reframes the entire idea of home in a cosmic sense. The Milky Way is not a bounded island we inhabit. It is a zone of gravitational coherence within a much larger system, a temporary structure maintained by ongoing dynamics, and its outer boundary is not a line separating it from the universe. It is a transition zone where its influence weakens relative to everything else. This is the conclusion modern astronomy is slowly converging toward. Not a final edge, but a hierarchy of scales, each with its own effective boundary, each valid within its own context, each incomplete on its own, and yet even this refined definition leaves something unresolved, because it still assumes that structure is the primary question, but a deeper question remains. If the Milky Way is not defined by its edge but by its influence, then what does it mean for a civilization to exist inside it? How does identity function inside a system without boundaries? How does meaning persist inside a structure that is always transitioning into something larger? This is where the story moves beyond astronomy and into civilization itself. Once the idea of a fixed edge to the Milky Way dissolves, something subtle but profound happens. The question stops being about the galaxy and starts being about the observer inside it. For centuries, humanity treated cosmic structure as something external. The Milky Way was an object above us, something to be mapped, measured, and eventually understood as a complete system with a definable boundary. Even when that boundary became uncertain, the assumption remained that there was still a whole galaxy to be described. But as models of the halo dark matter structure and gravitational interaction evolved, that assumption weakened. The galaxy is not a closed container. It is a dynamic environment, a continuously evolving gravitational field embedded in the local group shared with systems like the Andromeda Galaxy and countless smaller companions. And that changes what it means to exist inside it. Because without a sharp boundary, civilization is no longer situated within a clearly defined object. It is situated within a gradient of influence. That distinction reshapes everything. Imagine a future human civilization expanding outward from the solar system. At first, the sense of belonging is simple. Earth defines origin. The Sun defines local structure. The Milky Way defines cosmic context. But as expansion continues, ships move into regions where the stellar density drops. Navigation becomes harder. Gravitational influences become ambiguous. Signals from the galactic center weaken. The sky changes. There is no moment when the galaxy ends, only a gradual shift in the character of space. Stars become fewer. Distances become less intuitive. External galaxies become more prominent in the sky. And eventually the Milky Way stops feeling like a dominant structure overhead. It becomes one of many influences in a broader cosmic environment. At that point, identity begins to shift. Because civilizations do not only depend on physical location, they depend on reference frames, on what is considered center, on what is considered home, on what is considered outside. Without a clear edge, these categories become less stable. A civilization near the outer halo of the Milky Way might experience a sky where Andromeda is not just a distant galaxy, but a dominant gravitational presence shaping local dynamics. In such a region, cultural and scientific frameworks might evolve differently. The concept of belonging to a single galaxy may feel less meaningful than belonging to a gravitational neighborhood. Even time perception changes. In the outer regions, orbital periods become so long that galactic cycles lose relevance to daily existence. The Milky Way's rotation, which takes hundreds of millions of years, becomes an abstract background process, rather than a lived rhythm. Local stellar interactions become more important than global galactic structure. Civilization in this context becomes locally defined, not by the entire galaxy, but by immediate gravitational surroundings. This leads to a deeper realization. If there is no sharp boundary to the galaxy, then expansion into the outer regions is not a crossing into outside space. It is continuous extension into lower density versions of the same structure. There is no threshold where civilization leaves the Milky Way. There is only gradual reduction in its dominance, and that has philosophical consequences. It means that even as humanity spreads outward, it never truly exits its origin system. It simply moves through diminishing influence zones of it. At extreme distances, however, another shift occurs. The influence of the Milky Way becomes comparable to that of other galaxies within the local group. The sky is no longer dominated by a single galactic structure. Instead, multiple systems contribute to the gravitational and visual environment. The concept of a single home galaxy begins to fragment. Civilization no longer orients itself around one dominant structure. It orients itself around a network. This is where governance, culture, and identity begin to diverge. A civilization spread across such gradients would not experience a unified galactic identity. Instead, it would experience layered affiliations, local systems, regional clusters, gravitational neighborhoods, and broader cosmic structures. Each layer carries meaning. None carries absolute dominance. This is not a failure of unity. It is a consequence of scale. And scale in the universe does not preserve simplicity. It multiplies perspective. Yet even this vast civil structure is not stable in time, because the Milky Way itself is not static. It is moving toward Andromeda, slowly, inevitably, over billions of years. The future of the galaxy is not isolation, but merger, a gradual gravitational convergence that will eventually reshape both systems into a single larger structure. This means that any civilization existing within the Milky Way is not living inside a permanent object. It is living inside a transitional phase of cosmic evolution. The galaxy they inhabit is already becoming something else. And in that transformation, the idea of an edge becomes even more irrelevant, because edges belong to static systems, not evolving ones. In an evolving system, boundaries are temporary configurations of matter and influence. They appear. They shift. They disappear. This leads to a final reflection for civilization. If the galaxy has no true edge, then expansion is not movement from inside to outside. It is movement through degrees of belonging, through changing intensity of influence, through different configurations of the same cosmic environment, and perhaps most importantly, it reframes what it means to search for meaning in such a structure. Meaning cannot depend on boundaries that do not exist. It must emerge from relationships, from motion, from continuity, and from the recognition that civilization is not positioned at the center or the edge of anything. It is embedded within a system that has neither. Only transitions, only gradients, only change. And in that realization, the Milky Way stops being a map to complete. It becomes a perspective to inhabit. If you trace every thread of evidence, every stellar map, every gravitational model, every halo reconstruction, and every motion charted by missions like Gaia under the European Space Agency, a single pattern begins to emerge beneath all the complexity of the Milky Way. Not a boundary, but a refusal of the universe to be divided cleanly into inside and outside. For centuries, humanity searched for the edge of the galaxy as if it were a physical destination, a line drawn in space, a final threshold where stars ended and emptiness began, a place where one could in principle point and say, here. But the deeper we looked, the more that certainty dissolved. The visible disk faded gradually into a stellar halo. The stellar halo dissolved into a dark matter structure that cannot be seen directly, only inferred through its gravitational effects. That structure itself blended into the wider environment of the local group, where the Milky Way and the Andromeda galaxy are already locked in a slow gravitational approach that will unfold across billions of years. And beyond that, even the local group is not isolated. It is part of a filamentary cosmic web where matter stretches across intergalactic space in faint continuous threads. At no scale does the universe present a clean termination point. Instead, structure transitions into structure. Influence fades into influence. And definition becomes a matter of perspective rather than geography. This is the final transformation of the idea of an edge. An edge is what we imagine when we expect the universe to behave like human-made systems, cities, borders, maps, diagrams. Systems where separation is intentional and absolute. But the cosmos is not built that way. It is built through gravity, and gravity does not separate. It connects. Even the most distant regions of the Milky Way are still weakly tied to its mass. Even the faintest outskirts still respond, however subtly, to the pull of a structure spanning hundreds of thousands of light years. Even matter drifting in intergalactic space is not truly disconnected, but part of larger gravitational flows shaped by galaxies it may never fully belong to in a strict sense. So if there is no absolute separation, what remains? Only gradients, only transitions, only regions where one influence gradually yields to another. In that sense, the edge of the galaxy was never a physical location waiting to be discovered. It was always a conceptual boundary projected onto a continuous field, and as our instruments improved, that projection became harder to sustain. Each new dataset extended the galaxy farther. Each new survey revealed additional structure. Each refinement of dark matter modelling expanded the region of gravitational influence. The more precisely we measured, the less finite the Milky Way became. But something else happened alongside this expansion. Understanding deepened. Because losing a boundary does not mean losing knowledge. It means replacing one kind of understanding with another. Instead of asking where the galaxy ends, we learn to ask how it behaves. How stars move within its potential. How matter flows through its halo. How it interacts with neighbouring galaxies. How it evolves over time. And how its structure emerges from invisible scaffolding as much as visible light. The Milky Way stopped being a bounded object and became a dynamic process, a long-lived gravitational pattern embedded in a larger cosmic continuum. This reframing changes everything about how we interpret our place within it. We are not inhabitants of a closed system with an outer wall. We are participants in a vast evolving structure that has no final perimeter in the way we once imagined. Even the concept of leaving the Milky Way becomes ambiguous. A spacecraft drifting outward does not cross a sharp line. It gradually moves from strong influence to weak influence, from dominance to overlap, from one gravitational regime to another. At no moment does the universe announce that a transition has occurred. There is no signal, no border post, no final threshold, only continuous change. And perhaps that is the most important realization of all. The absence of an edge does not diminish the galaxy. It reveals its true nature. A system defined not by separation but by continuity, not by enclosure but by interaction, not by finality but by evolution. In that light, the Milky Way is not a place we stand inside. It is a perspective we pass through, a transient configuration of matter, gravity and time embedded within a universe that itself resists clean definition. And as we step back from the desire to find its edge, something subtle replaces it, a quieter understanding that the question was never truly about where the galaxy ends. It was about how far human understanding can extend before it too becomes part of something larger. And in that sense, the edge we were searching for was never out there in space. It was in the limits of our expectation that the universe should have one. Now that expectation has dissolved, and what remains is something far more expansive. Not a boundary, but a continuity stretching outward without end.